know this computer mumbo jumbo stuff. So I asked the people who are involved in technology transfer or whatever it's called, and they tell me that you can all log on to something called e-class, and if you then select the course number, there is a forum, and apparently you can write something in the forum like, I didn't understand the valency of carbon is 4, can anybody help? And someone else will write, yeah, it is 4 because that's what it says in the book. So apparently you can do this sort of thing, and so I've had it set up, and the person who set it up told me that if I type in this thing called a URL, and then put in my CCID password, then I will be able to see what is written. So I'm not going to do that. So you have now a forum, and so if any of you want to sort of pose questions and others answer, that's fine. If you've got serious questions, you've got to ask the help session people or ask me. The reason why I make such a joke about this, if I looked at this, there are 253 of you, and you know, if I spent just 1 minute on each, I wouldn't have any time to eat or sleep or do anything. So I obviously can't do that, but if you want this sort of thing, that is fine. The next thing is that there is an exam, a midterm exam coming up on October the 17th, and I only realised that the other day, so I started to set the questions. I only set 3 of them because when I looked at them, they were so hard I fainted. They're not really that hard. But what I'd like to do is I'd like to give a super TA help session before the exam, which tells you, which I will tell you because I'm a super TA, of course, with the emphasis on super, that I will tell you the sorts of questions that are in the exam. I won't give you the exact questions, but I'll go over all the things that you need to know. One thing I will also do, and I'll tell you this now, is I will give you 2 little tables of NMR chemical shifts, and one of them of NMR chemical shifts and one of them of infrared frequencies, and I had to type that out myself on Saturday night instead of going downtown and having a few beers and a good time. I had to stay in my office and type this out because the new copyright laws prevent me from Xeroxing it from your book and giving you a copy, otherwise I'll go to prison. Then you'll all do badly in the exam because I had set the exam, you wouldn't have had the lectures. So I typed it out, and I'll give that out. The reason why I'm telling you this now is I don't want you to waste time trying to learn these numbers. So you'll have a little table, it's only 1 page. So that will help you. And I just copied it, I just typed it, didn't copy it. I typed it and changed the format somewhat from the information given in your textbook. So that's the first thing. So we've got to decide on a time for this help session. Now the exam is on Monday the 17th, and so I suspect that the week before that, one evening at either 5 or 5:30 would be the most ideal time from the point of view of helping you. Now, first of all, let me ask, is 5 more convenient than 5:30? Some of you have, or 6, some of you have labs. I don't know when they end. The labs end at 5? Sorry? 10 to 5, so 5:15 you could all, and I don't know which room they'll have it in, but once I know the date I'll ask the booking people to choose a room. Hopefully they can choose a room, otherwise we'll have to have a tent out in the quadrangle and do it in there. Okay, so say 5:15 would be a good time. The next thing is which day Somebody said Friday. Well, then, you know, I'm not... It's absolutely impossible for me to choose a day that's optimum for every single one of you. So hopefully, by a show of hands, it'll be clear. Now, so let's start at what I suspect is the worst day for you. I don't know why that should be, but perhaps there's some social activities, I don't know. Friday the 14th. There's only a very small number of people. Thursday 30.
Yeah.
That's a more sizable number. Wednesday the 12th. I think Thursday beats Wednesday. Tuesday the 11th. It looks like Thursday. Can we have a show of hands for Thursday again? Yeah, okay. Okay, what I will do is I will ask the timetabling people to get me a big room. Hopefully it's this room, because I like this room. It's near to my office. It's got nice boards, and apart from the unwarranted height of this, it's a pretty good lecture theatre. So I've done the help session stuff. I told you to give you little tables. There's one other business, but I suspect we can probably do this after the exam if you like. I did miss one lecture, so I must give you a make-up lecture, which likewise will be at the same time. So, do you want it before the exam or after the exam? Won't make any difference to the exam. After, yeah, I thought so. You know why? Because there's less material for the exam to be covered. That's your logic. But you see, I think it was adjusting. That just made the questions harder. I'm not going to do that. I'm way too kind. Honestly. Okay. What I have to do now is to continue talking about aromatic compounds. You remember that in the last lecture, I pointed out that there are a number of some. Yes, you have a question?
Yes. Are you going to post a practice midterm before the test?
No, I can't because I haven't given this course before. Oh. I assure you, that doesn't mean that I don't know what I'm talking about. You know, what I give you in this health session will constitute a practice midterm, because I'm going to tell you what sort of questions you're going to get. For example, you're not going to get this because this is from the first term course, but supposing question 1 was how to calculate the molecular formula from the percentage composition. I would just tell you, you need to know how to calculate the formula from percentage composition, and here's an example, and I'll work one out. And obviously in this exam I'm going to give you some NMR data. And so I'm going to go over how to use NMR data to work out the structure. And there'll be a very little bit of use of infrared spectroscopy, but very little bit, because if the molecule has got one double bond equivalent, I might tell you it shows a strong infrared absorption at 1725, you would look at the little table and say, oh, it's not an alcohol, it's a carbonyl compound. And then taken together with the NMR data, that will enable you to work out what the structure is. So don't worry, I want you all to get a high mark. It's much easier to mark exams when they're all correct. And of course, if they're all wrong, I get into big trouble. So don't worry, you're well protected by other factors. What I was doing last time was to point out to you that there are a number of compounds that in the old development of organic chemistry were called aromatic compounds. Some of cinnamaldehyde is an example, but there are others, and the word had its normal meaning, they smelled nice. and that many of them were found to contain a certain structural unit, which is a six-membered ring. And aromatic compounds are in fact compounds that have this six-membered ring in it, but it's not a saturated ring, it's not cyclohexane. These compounds are all derivatives of a substance called benzene. And I'm going to draw up one of the representations of benzene. I'll fill in the hydrogens for you. And at this moment, I won't tell you exactly what this picture means. As many of you, perhaps all of you, should know, it does not mean alternating single and double bonds. But benzene is a substance, it's C6H6. I might tell you was first isolated by that famous Englishman Michael Faraday. That won't be on the exam. So these substances are all derivatives of benzene, or many of these aromatic substances are derivatives of benzene in which one or more of the hydrogens has been replaced by something else. So we need to know how to name these compounds. And if you have a very simple one, I'm going to, well, I'll draw it like this. This substance is called fluorobenzene. And of course you won't be surprised if I tell you that that substance is chlorobenzene. But I'd better write this one out in full. This one is nitrobenzene. So you can see that for simple compounds, certainly for compounds that just have one substituent on them, one of the ways of naming these things is to indicate in the beginning of the name what the substituent is. Is it chlorine, bromine, iodine, fluorine, or is it a nitro group? And then you stick that piece to indicate what the substituent is onto the name benzene. Now there are a number of benzene derivatives that have their own trivial name rather than a systematic name. This is called toluene. This is called phenol. That is called aniline. There are a few of them. I'll give you just maybe three more. That's benzoic acid. That compound is acetophenone, and the last one that I'll give you anisole. Now, there are a good many others that have their own trivial names, but this is enough for our purposes. So another way of naming compounds is to recognize that the compound is one of these that has its own trivial name. Now, all of these substances have one substituent on the benzene ring. You can imagine that each of these has been made by somehow taking benzene, removing one of the hydrogens, and replacing it by the substituent. So these are mono-substituted benzenes. Now, there are 6 positions on benzene, so in fact you could have a disubstituted, a tri, a tetra, a penta, and a hexasubstituted benzene. And when you have more than one substituent, then there is a little bit of a problem that you have to overcome. It's very easy to overcome in naming the compounds, because not only do you have to indicate what the substituents are, but you have to indicate where they are relative to one another. So I want to show you how to do that. So let's take it in small steps. Let's consider di-substituted benzene compounds. And just to make things easy, I will use 2 substituents that are the same. So just as in the book, remember I'm on chapter 14 now, and I'm certainly not going to do the whole of chapter 14. It contains a load of stuff that you don't need to know. So all these are dibromobenzenes, and you can obviously understand, I'm sure, why they're called dibromobenzenes, because there are 2 bromines that are attached to the ring in place of the hydrogens originally on benzene. And when the 2 bromines are next to one another, we call strange. There must be a pickup mic somewhere that in certain positions makes this stuff not work properly. When the 2 bromines are on adjacent carbons, we call that compound ortho-dibromobenzene. Ortho just means on adjacent carbons. When there's a carbon space in between, it's meta-dibromobenzene, and when there are 2 carbons in between, it's para-dibromobenzene. So all of these are isomers of dibromobenzene. They're structural isomers. They all have the same molecular formula, but the atoms are joined in different ways. So you have the ortho. I'll write that word out in full. Usually one doesn't write the word out in full for ortho. You just put a little italicized O, and a little italicized M, and a little italicized P in front of the name. But there is another way of numbering these things, and the way to number them is to start at one of them and call this 1,2-dibromobenzene. And of course, having told you that, it's a no-brainer to realize that this is 1,3-dibromobenzene, and likewise that's 1,4-dibromobenzene. So when you have 2 substituents, you can either use the prefix O for ortho, or N for meta, or P for para, or you can use 1,2, or 1,3, or 1,4. Now, notice that I could number this if I wanted to be awkward. 1, 2, 3, 4, 5, 6. There would be 1,6-dibromobenzene. But the way you do it is you start at one of the substituted positions and you give that to number 1, and then you go around the ring in such a direction that the next number you come to is as low as possible. So clearly, if I call one of them 1 in this case, then the next one's got to be 2, because if I go around the ring the other way, the next one gets the number 6. So you always go for the smaller number. Now, if you have a di-substituted benzene in which you can recognize one of the compounds that has its own name, let's take this for example. If I cover up the nitro group, you recognize it's a substance commonly called benzoic acid. So this one could be called meta or 3-nitro benzoic acid. So when you have a name that you recognize, then very frequently you take that name and then you put in front of it the name of the substituent plus an M or an O or a P or a 2 or a 3 or a 3 or a 4. There are a few more that you need to know. This is called orthoxylene or 1,2-dimethyl benzene. And of course, it won't come as a surprise to you if I tell you that there's another one called metaxylene or 1,3-dimethylbenzene, and there's also another called paraxylene or 1,4-dimethylbenzene. By the way, the pronunciation of this word is xylene, as though the first letter was Z. Don't try and pronounce it as an X, like xylene. You can't pronounce that. It's xylene, as though it's a British Z. Now, if you have, so this is some of the ways of dealing with di-substitute benzenes. If you have tri-substituted benzenes, you must use numbers. So for tri-substituted benzenes, you don't use ortho and para. The reason for that is that supposing you say para, but you've got 3 substituents, then the question immediately, the confusing question comes, okay, so which substituent is para to which other substituent? That just leads to confusion. So you use numbering. Now this is clearly a tribromobenzene, but what isn't so clear is what are the numbers going to be? Well, the rule is that you start at one of the substituted positions and you number around the ring such that the numbers that you get allow you to give the lowest possible number to the second group that's mentioned, and if there's no difference at the second group, then you go to the third group, and if you've got a tetrasubstituted benzene, you may have to go to the fourth group. Now, that sounds a little bit complicated, so let me explain. I could start numbering here. If I started numbering here, I could go around the ring that way or this way. Let's start numbering and go around that way. 1, 2, 3, 4. So it would be 1, 3, and 4. Supposing I went round the other way, it would be 1, 1, 4, 5. Supposing I start numbering here and go around this way. It's 1, 2, 4. Supposing I start numbering here and go around that way. It's 1, 4, 6. Supposing I start here and go around that way. It's 1, 2, 3, 4, 5. Supposing I start here and go around that way. It's 1, 3, 4, 5, 6. Okay, I think I've covered all the bases. If I haven't, I've covered enough of them to tell you exactly how we do it. In every single case, it's very easy to apply the rule. One of the substitute positions becomes number 1. So the first entry in every single case is 1. So I can't choose between them. So now I'm going to go and consider the second entry in every single case and find out which, if any, is the smallest. Well, clearly 2 is smaller than 3, smaller than 4, smaller than 4. So all these can go. I can't choose there, but this can go. So I'm now left with choosing between 1, 2, 4 and 1, 2, 5. So now I go to the third entry. And of course, this one wins. So in fact, it is 1, 2, 3. That's the way to number it. So you give, what they say in the book, the lowest possible numbers to the substituents. But by lowest possible numbers, what they really mean is you consider all the possible ways of numbering the thing, and you put the numbers in ascending order, from small to big, to bigger, bigger, so on. And then you compare the first entry in every case. If you can make a choice at that stage, fine. If you can't, you go to the second entry in every case. If you can make a choice at that stage, again, fine. And if you can't, you go to the third entry. And you keep doing that until you find the set of numbers where at the first point of difference from the other numbers, you have the smallest possible one. So that's the way to name those things. Now, if you have substituents of a compound that you recognize as one that has its own trivial name, if you look at this, you'll see that this thing is something called benzoic acid. You should be familiar with benzoic acid. If you go to the supermarket and you buy some packaged foods, you look at what's on the ingredients, you'll frequently see sodium benzoate, which is the sodium salt of that acid. There's so many chemicals in some of these processed packaged foods that I think you could get just as much nourishment by going down to the chemical stores and browsing there. So this thing you can regard as a derivative of benzoic acid, and if it is, then you must give 1 to the main functional group that identifies the substance. So this now is 3,5-dinitrobenzoic acid. Dinitrobenzoic acid. There are a few more bits and pieces with respect to naming. This group, if it's on something else, is frequently called a phenyl group. And it's abbreviated either as pH. So pH means C6H5, this benzene unit stuck onto something, or it's also abbreviated by that symbol. So if, for example, if I have this substance, and I was in a hurry, I could write it like that, or I could write it like this. Now what happens if you have one of these phenyl groups attached to a chain? Well, if it's attached to a saturated chain, it's usually butyl benzene. So you regard the chain as a substituent. So if it's a 2-carbon chain, it would be ethyl benzene. If it was a 3-carbon saturated chain, it would be protyl benzene. It's a 4-carbon butyl benzene. It's 5-carbon pentyl benzene, and so on. If, however, the chain is unsaturated, then very often the compound is named by naming the unsaturated chain and regarding the benzene ring as a substituent. So I'll show you how that works. That's one of the names that can be given to that substance. Notice what I'm saying. I said a moment ago, these things are usually named by naming the unsaturated chain and regarding the benzene ring as a substituent. And I've just said that this is one of the names that can be given to that substance. And the reason why I have to say that is that there is no one single way or naming system that's followed by everybody. If you look up a publication called Chemical Abstracts regards this as a derivative of benzene. So it's benzene carrying this substituent. It's a 4-carbon substituent. When you see a 4-carbon substituent, you think of butane, but this is an E. So you think of butene, but it's a substituent, so it's a butenyl. Where in the butenyl unit is the benzene ring attached? Well, it's attached to position 2, 1, 2. So according to Chemical Abstracts, this thing would be 2E, U2enyl benzene. So there are a number of ways of naming these compounds. Now, what's so special about benzene? Obviously, there's something special about it because I've made all this song and dance. It's an aromatic compound, and people notice the so-called benzene subunit in many compounds in the early days of the subject that had a nice smell. And I've told you that the naming is not so simple. I've given you some of the rules so you can make you can assign a sensible name to these compounds. What's so special about them? Well, there's something very special about them because if you write down and interpret without any other knowledge the meaning of this picture, so-called Lewis structure, where a single line means 2 electrons shared between 2 atoms, 2 lines mean that it's got pure orbitals overlapping. You have a question?
When you have a benzene ring as a substituent, like you only count it as a substituent if like the chain is longer than the amount of carbons in the benzene ring, right?
Yeah. You can have 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. So suppose you have 5 carbons, there's less carbons than in the benzene ring, that's still pentyl benzene.
No, in the chain.
If you've got 10 carbons, then it's decyl benzene. Okay? That's the way it is, that's what people do. What can I do? If you interpret this picture strictly, you would have to say that it's a ring in which there are alternate double and single bonds around the ring. And so, for example, you would expect this to have the properties of double bond compounds. And you know, for example, if you take ethylene, you add bromine, you get 1,2-dibromoethane. But if you add bromine to this in the dark, you certainly don't get that. Another thing that you would imagine is that if you compare this with, say, this compound, and do a hydrogenation with a catalyst, you get cyclohexane. Now you can actually measure how much heat is given out in the hydrogenation of cyclohexane, and that's one double bond. And so if you hydrogenate benzene to give exactly the same thing, which requires more vigorous conditions, and as soon as I tell you that, you realize, oh, there's something funny about those double bonds. Why should they require more vigorous conditions than for cyclohexene? Well, if you do the experiment and you make cyclohexane, you would expect 3 times the amount of heat to be given out as you did in this experiment, because there's 3 double bonds. But if you do that experiment, you'll find that you get out much less heat, a lot less heat, 36 kilocalories per mole less. So there's something funny about these double bonds in benzene. It behaves in a different way from what you'd expect if there were ordinary double bonds. And the compound is actually a lot more stable than if what looks like double bonds were real double bonds. And there's some more problems. What you should do at this stage is to do review problem number 14.2, which is the same 14.2, and it's equivalent to 14.1 in the 9th edition. Okay, now let me tell you some more problems associated with this structure. Let me first clean some board. So 14.2 and 14.1. 14.1 in the 9th. One of the first people to write a useful structure for benzene was somebody called Kekule, who wrote this. Now, if this is the structure with seemingly alternate double and single bonds, you should get 2 different orthodibromobenzene, because one of them would be this, and you could actually write another one like that. And you can see these are different, because here the bond between the 2 carbons carrying the bromine looks like a single bond, here it's a double bond. So there's something wrong with the Kekule structure of benzene. And as I've told you, that fits in very nicely with the fact that if you hydrogenate the 3 what look like double bonds of benzene, the amount of heat you get out is 36 kilocalories per mole less than if you hydrogenate 3 ordinary double bonds. And so, what's the real story? Well, the real story can be discussed in 2 different ways. One of the ways is the resonance structure method. Let me show you what that is. What we do is we draw two pictures for benzene in which the only difference between them is we have moved pairs of electrons. It's the only difference. We have not altered the geometry, and for the geometry, what we will do is we will draw a regular hexagon of the size of benzene. And what we say is, we know what the shape of benzene is, so we know its dimensions, it's a flat regular hexagon. We know that all the carbon-carbon bonds are the same length, so none of them is a real single bond, none of them is a real double bond. We know all the CH bonds are the same length. And then we say we cannot depict that situation by using these line diagrams. So what we do is we draw two line diagrams that are totally hypothetical molecules, and we say that the actual molecule is a blend of the properties you'd expect for these two. So this has the dimensions of true benzene, but we have artificially made these two p orbitals overlap. We've artificially made these two overlap and these two, and we have not allowed any overlap between the p orbitals here and here. So it's all artificial, that can't exist. So these are hypothetical structures, they are called resonance structures. And they are joined by a double-headed arrow. Notice this arrow, it is not that, but is in fact this. So that's all wrong. So we've got a situation here where we know that the compound we're trying to represent cannot be represented by these line diagrams, which are actually Lewis structures. But it's very convenient for us to use these line diagrams. You'll see in a moment that it's incredibly inconvenient to use a diagram that represents more accurately what's going on. So because it's so convenient to use these diagrams, we use them. But we bear in mind that they do not represent reality. And each of these diagrams is a resonance structure, as we call it, and the actual properties of the molecule are what you would expect from, in this case, an average of the two resonance structures. These two resonance structures have the same energy. Now, there are other molecules in which the same situation occurs. You can't properly use the line diagrams to represent what's really going on. Remember I told you the other day about butadiene? There are other molecules in which there's more than two resonance structures, and some of the resonance structures are more important than others. So the actual properties of the molecule is a weighted average of the properties you'd expect for each of the resonance structures. Now, in case of benzene, it's easy. They're just two structures that are really important. When you draw resonance structures, they must have the same geometry. Now, there is another way of representing this situation. Or there are two other ways. You can either write this every time you want to write a reaction about benzene. That would take up a load of time. Or you could write this, or just this, or just that, and bear in mind, assume that your readers, and of course you yourself, realize that it's a shorthand and you're just writing one of the resonance structures. Or you can do this. And that circle inside a ring means 6 electrons delocalized over the perimeter of the ring. And you'll see in a moment when I draw up the molecular orbital picture for benzene that in fact there are 6 electrons delocalized over the ring. Now, because you know what the shape of benzene is, regular hexagon, and all those carbon-carbon bonds have the same the same length, each of the carbons is sp2 hybridized. And so if I draw some sort of orbital picture and just put in the p orbitals on each carbon, of course, for each carbon I have one p orbital. And you can see that this p orbital, so the p orbitals overlap above and below the plane of the ring. So if you imagine one of these, you could buy some sort of cookies at these Tim Hortons, a place like that, which is a circular piece of dough. What's it called?
A donut.
I don't know these things because, you know, my butler and the main kitchen staff prepare all these things for me as my residents. There's a donut of electron density above and below the plane of the six-member ring. And of course, when you think of it that way, you can understand that all the carbon-carbon bonds are the same length. So there's a donut of electron density above and below. But the situation is more complicated because, as I told you when I dealt with butadiene, if you combine two p orbitals, you have to get two molecular orbitals. Likewise, if you combine 6 p orbitals, you've got to get 6 molecular orbitals. And each molecular orbital can hold only 2 electrons. And in fact, the molecular orbitals of benzene, they all, just as in the case of butadiene, they have different energy levels. And here they are. So you put 2 in there, 2 in there, and 2 in there. So these are the filled molecular orbitals of benzene. So by telling you that there's a donut of electron density above and below, I haven't sort of forgotten that in fact with molecular orbitals you can only put 2 electrons into each orbital. Nonetheless, if you could see the electron density, you would see a donut of electron density above and below. But it isn't all the 6 electrons in the one orbital. So that's an orbital picture of benzene, and you can see now from that very simple picture that in fact, because of the delocalization of electron density all the way around the ring, you can understand why all carbon-carbon bonds are the same. Now, as I said, there's something very special about benzene. It's more stable than it would be. And whenever you can write resonance structures, the compound is more stable than if you couldn't write resonance structures. You can write 2 resonance structures. Are there any other compounds that have the same feature, in other words, delocalized electrons around a ring, that are more stable than you'd otherwise expect? And the answer is yes, and there's somebody called Hooker who discovered that if you have a planar ring with p orbitals such that the number of electrons in the planar ring is 4n plus 2, that substance will be aromatic. In other words, it will have these peculiar properties of benzene, more stable than you'd otherwise expect. It would have reactions that aren't the same as forming double and single bonds. And you can see that benzene has 6 of these electrons, and 6, if 4n plus 2 equals 6, that means 4n equals 4, that means n equals 1. And so benzene is the most famous example of what's called the Hooker rule. You spell Hooker with 2 dots on top of the U. It's a German name. That mark is called an umlaut, if you speak German. Looks to me like I only had 2 or 3 seconds left, so we better stop.